Good evening, everyone. Can you hear me? Good evening, everyone. Can you hear me? Today we are going to start, that is the initial rate of change of voltage or current. Earlier we have studied, for a capacitors voltage cannot be changed instantaneously, and for an inductors current through the inductors cannot be changed instantaneously. Okay, let us consider the given circuit. This is your capacitor C and the value is 10 microfarad. Okay, and VC0 minus is equal to 10 volt as the, so this is the VC, and there is a switch. This is the R, which is equal to 2 kilo ohm. At t equal to 0, switch is closed, right? At t equal to 0, switch is closed. We need to find di, that is I0 plus di upon dt 0 plus Vc 0 plus dv upon dt 0 plus, you can also further proceed, d square I upon dt square 0 plus, etc. As I have told, I want to confirm whether it is audible or not. Is it audible? Am I audible? I want to confirm whether it is audible or not. Okay, it is audible, I can hear it. So for t0 minus, this is the, for t0 minus, Vc0 minus is equal to 10 volt, I 0 minus 0 ampere. It is clearly seen because at that time switch is not closed. So when just after the switching or switch is closed at t0 plus, right, as you know, the voltage across the capacitors cannot be changed instantaneously. So this is a capacitor, so both Vc0 plus will be remain 10 volt and I0 plus will be the 10 volt upon 2 kilo ohm, that is 5 milliampere. The circuit looks like this. It's a voltage source and R. So this is your I. So R is equal to 2 kilo ohm. A voltage source 10 volt. Right? Okay, we got the I0 plus 5 milliampere, VC0 plus 10 volt. Now the question is how to find this initial rate of change of voltage across the capacitors and current through the resistors. For that, you just write the dynamic equation of the circuit after switching. This is your R, this is your C, this is your VC, this is your I. Clear? Yes or no? So you can easily write I is equal to C dVc upon dt, negative sign because current is flowing opposite to the voltage source one, because you know that dynamic equation for the capacitor, when it is I and this is your Vc, then we write I equal to C dVc upon dt, but it is showing opposite here. So now I can write dVc upon dt is equal to minus I upon C, and dVc upon dt at 0 plus will be minus, what is the variable here, I0 plus upon C. So put the value. What is the I0 plus? I0 plus was the 5 milliampere, so 5 10 to the power minus 3. And what is the value of the capacitors? 10 microfarad, so 10 into 10 to the power minus 6. So you can say that it is 0.5 into 10 to the power 3. Okay, 0.5 into 10 to the power 3 volt per second. At this rate, that is, you can also write 500 minus 500 volt per second. At this rate, it is changing. That means the voltage at initial rate of change is a minus 500. That means the initial slope of the curve is minus. That is the, like, this will be like this, the your VCT. So this slope is, obviously this slope is minus 500. Clear? So first find the initial values. So once again, first find the initial values. It is the given values at t0 plus, using your the concept learned in the last class, that is the voltage across capacitors cannot be changed instantaneously. So you find the voltage, then initial current, then this is the further t0 plus circuit, then then write the dynamic equation of the circuit. Then after writing the dynamic equation, find out the rate. If you don't have any dVc upon dt, then you just do the manipulations to get the this rate of change of things, and put the values at 0 plus, and you will get this, right? Now come to the how to find di upon dt. Okay, di upon dt. So I can also write KVL here. See, from this circuit I can write the KVL. So if you know the KVL, how to write the KVL, which is equal to RI, this is the because the current is flowing, so RI and this is the current flowing, this will be positive answer, plus 1 upon C integration of I dt equal to 0. Just when this current is circulating this, so this is positive, negative, this is positive, negative, just traverse any of the ways and find the write the KVL and you will get these equations. RIC, I am traversing from negative to positive, so RI, then from negative to positive, that is 1 upon plus 1 upon C integration of I dt. Now I will differentiate it, so R di upon dt plus I upon C equal to 0. So di upon dt is equal to minus I upon RC. Clear? Now it is time to put the value at 0 plus. So di upon dt at 0 plus minus 1 upon RC I 0 plus. So you can find out. So minus, so what is your R? R is the 2 kilo ohm. C is the 10 into 10 to the power minus 6. And I is your I0 plus is the 5 milliampere. So 5 into 10 to the power minus 3. So ultimately you will get C, this minus 3, this minus 3. So minus 5 upon 20. 5 upon 20, that is minus 1 upon 4, that is minus 0.25 ampere per second. Hope you got it. Now question arises, okay, this is the second derivative, the initial rate of change. Suppose we want to find the d square I upon dt square, right? Very simple. You see here, just again differentiate this equation, that is d square I upon dt square is equal to minus 1 upon RC di upon dt. Now d square I upon dt square at t equal to 0 plus, which is equal to minus 1 upon RC di upon dt 0 plus. So same way, put the values. R is the 2 kilo, 10 to the power 3, 10 into 10 to the power minus 6, and you got here minus this value di upon dt 0 plus. So you got 0.25, right? So you can see that 10 to the power 3 into 10, that is 10 to the power 4. So in the top it got go 100, so minus minus positive, so 25 upon 2, which is equal to 12.5 ampere per second square. Amperes per second square. Clear? Similarly, if you want to find d square Vc upon dt square 0 plus, so you can get also that. We know that dVc upon dt equal to minus I upon C. We know that dVc upon dt is equal to minus I upon C. d square Vc upon dt square, that means differentiating again, minus 1 upon C di upon dt. So d square Vc upon dt square at t equal to 0 plus is equal to minus 1 upon C di upon dt 0 plus. Just now we got the what is the value of di upon dt 0 plus. First use the 1 upon c, that is 10 into 10 to the power minus 6 into di upon dt at 0 plus. Di upon dt at 0 plus is the minus 0.25. Okay, so minus 0.25. So minus minus plus, that is 0.25 into 10 to the power minus 5, right? That means 25 into 10 to the power 3, sorry, this is, yeah, 10 to the power plus 5, plus 5, 10 to the power 3 volt per second square. You can easily see that the general shape of the response. You can easily see that whenever you have a capacitors have some voltage 10 volt and you have a switch, you have a resistors, you close the switch at t equal to 0. So if you want to draw vc or I, okay, so it is the curve, general curve will be the simply, suppose vc, that is your 10 volt initially, so it will be an exponential decaying and 0, ultimately 0. This is your vct, and similarly current will be also 0 when it is completely discharged. So initial current is your 5 milliampere. This is your current I in milliampere. This is your 5, this is 0, and this is your 3. So this is the general shape of the response or current or voltage of above circuit. Hope it is clear. We will next move to the some other questions, or we can say the finding the response, because till now we have studied point values, that is the t0 minus, t0 plus, the response at t0 plus or response at t infinity, but we have not yet covered the for whole range, that is t greater or equal to 0, what will be the response. So response of circuit for t greater or equal to 0. We'll again take that example. You have a capacitors, you have a switch, and it is closed at t equal to 0. You have a resistors, capacitors initial voltage, that is Vc0 minus is equal to, this is your Vc, and this is the capacitor C, this is closer to equal to 0, and we need to find Vct I t for t greater or equal to 0. R value of R is equal to 2 kilo ohm and C is equal to 10 microfarad. Okay, what we are going to find, that is the total response. So for that you should have little understanding of the differential equation, because I am not going to use Laplace transform now. Okay, so we know that I is equal to this I is equal to Vc upon R. Am I right? Okay, if I am right, let it be equation 1. Also we know this I is equal to minus C dVc upon dt, equation 2. Combine both the equation, that is I in place of I, or use one equation in other. In place of I, I'll write Vc upon R and plus C dVc upon dt equal to 0, and dVc upon dt plus, take out C common, so 1 upon RC Vc equal to 0. Can you identify this equation? This equation is a linear differential equation, first order differential equation, linear constant coefficient differential equation, right? So if you know this is the linear constant coefficient linear differential equation, you also know the what is the particular integral. Either way you can do. I will suggest you go for the PI and CF, particular integral and complementary function. So PI auxiliary equation, first calculate the auxiliary equation, S plus RC equal to 0. So pole, or you can say the roots, is the minus 1 upon RC, and complementary particular integral PI, so I can write VCT1 VC1, because for PI particular integral is the one second, let me check PI CI. Sorry, this is the complementary function. Yeah, natural response, we called it complementary functions, right? I was earlier right. So no, just only nomenclature. So complementary function is the form of, that is k1 e raised to the power st, which is k1 e raised to the power minus 1 upon rct, and particular integral is called the forced response, because you don't have any input here in the differential equation. So Vc2t equal to 0. So Vct is the summation of complementary functions plus particular integral. So it is simply k1 e raised to the power minus t upon rc. Now question is how to find k1. It is well known, because you know the initial value of the voltage across the capacitor, which is 10 volt, So put these values at t equal to 0, which will get you the k1. So 10, put this value at t0 plus, is equal to k1 e raised to the power minus 0 upon rc, which is k1, and which means your K1 is equal to 10. So finally the VCT is equal to 10 e raised to the power minus t upon RC. So find the RC. RC is equal to 2 into 10 to the power 3, that is the value of resistors. Good evening, Hers. And 10 into 10 to the power minus, that is 10 microfarad. That is 2 into 10 to the power minus 2. That is 1 upon 50. So your VCT equal to 10 e raised to the power minus, if RC is the 1 upon 50, so 1 upon RC will be the 50 T. 50 T for T greater or equal to 0. And if you want to find that is your I T, it is very simple, that is VCT upon R, that is 10 e raised to the power minus 50 T upon R, that is 2 kilo, which is 5 e raised to the power minus 50 T milliampere for T greater or equal to 0. Very simple. So whenever you are dealing with this is called the single time constant circuit, because you have only one energy storing element, or combination, when you combined it, it behaves as a one energy storing element. So that's why it has the only a single time constant. Okay, mostly you will get the questions can have more than one time constant. So for that you need to solve the second order differential equations. So instead of dealing with the differential equation, there is another way, that is use of Laplace transform in the circuit. That will be covered in the next class. But before concluding the today's that is your topics, you can, for a single time constant circuit, you can, instead of solving this, okay, instead of solving this, for single time constant circuit, you can write the equation. The precondition is the first is the circuit direct relation. Okay, circuit must have single time constant. Time constant. The precondition 1, 2 is the input is step. Input is step change in either voltage or current. Step change in voltage or current, right? So you can use the relations like this, any for anything, any variable, whether voltage or current. I will write like this: x of t is equal to x of infinite minus bracket x of infinite minus x of 0 plus e raised to the power minus t upon tau. What is this? The values x of t, that is for all values greater than equal to 0, because we are we are doing a change or switching action takes place at t equal to 0. Switching takes place at t equal to 0. So this is the x of infinity is equal to value of x of t at t tends to infinity. X of 0 plus is the value of x of t at t equal to 0 plus. Tau is equal time constant. Now question is how to determine the time constant for the single energy storing element, okay, or that's why I call the single time constant circuit. Very simple way you should follow that. Suppose you have a circuit like this. That is, after switching the circuit becomes like this. Then reduce this voltage source or current source to 0. Here voltage source, when I reduce the voltage source, the situation is like this. Okay, this is R and C. So look from the energy storing element. This is the just box it, energy storing element. Then look from the what capacitor sees. So you can see that R equivalent, the capacitor sees, that is views or capacitors from the from the capacitor looking into the circuit, or you can say just cut the capacitors and find the Thevenin resistance, like that you can say. So R equivalent is always found out from the angle of C, that is capacitor. So you can easily see that R equal to R, and C equivalent single energy storing element, that is a single capacitor here, that is C. So time constant for this circuit is the R equivalent, C equivalent, which is RC. And in similar fashion, suppose you have a voltage source, and because another energy storing element can be inductor, reduce the source to 0. When I reduce the source to 0, that is, this is the method of heading is method of finding time constant for single time constant circuit. So I can reduce the voltage source to 0, so circuit becomes this. Same way you look from the inductor and find R equivalent, which is R. Then find L equivalent, which is L. So time constant for RL circuit is L equivalent upon R equivalent, right, which is L upon R. Okay, these are the simple circuit. Let us try to find some other circuit to find the discuss the other circuit to find the time constant. Okay, tell me what will be the time constant of this circuit, that is R1, R2, R3, C. This is the applied voltage. So, So as I have told, reduce the voltage source to 0, disconnect the or loop from the capacitors. That means circuit is simply, this will be the C parallel R2 parallel R3, this is your R1, this is your C. This circuit, when I see from the capacitors, my R equivalent will be the R1 plus R2 parallel R3, and C equivalent is equal to C. So the time constant will be the R equivalent, C equivalent, that is C into R1 plus R2 parallel R3. Okay, so let's do another example which have more number of capacitors or inductors. For example, this circuit. So we, after switching, circuit is, look, after switching, after t0 plus, after t greater or equal to 0, switch looks like this. After switching, circuit look like this. This is your C1 and this is your C2. Okay, what will be the time constant of this circuit? As I have told, reduce the voltage source or current source to 0. When I reduce the voltage source to 0, this will be shorted. So when I look from energy storing element, R equivalent will be the R1 parallel R2 parallel R3, and C equivalent is the series connection of this capacitor C1 C2. As you know that series connection C1 C2 upon C1 plus C2. So time constant is the R equivalent into C equivalent. Okay, time constant is the R equivalent, C equivalent. Okay, after learning this, how to find the time constant, let us go for the example how to directly use the relations, because this type of questions will always come in the GATE or other engineering competitive exam. Also, it will be applicable in your digital VLSI circuits, like finding the timing, different timing, and even the analyzing the transient in the operational amplifier, or in the other where you require the transient, that is switching, then switching takes place. For the pulse circuit, pulse shaping circuit also you need to do, and they combine both the things to get the to ask you a question in the GATE exam. Let us, you have a circuit C, okay, which is and initial voltage is the 10 volt. This is the capacitor C. C equal to something different is given. Okay, and you have a switch here. You have a R, 10 kilo ohm R, and switch is closed at T equal to 0. You need to find this IT for T greater or equal to 0. Find IT for T greater or equal to 0. Okay, so C equal to 100 microfarad. C equal to 10 microfarad. Sorry, C equal to 10 microfarad. And the charge polarity, the capacitor has some initial charge, that is with this polarity. So Q0 is the 100 microcoulomb. Okay, these are the data. So first find the VC0 minus, VC0 minus, you know that this is the charge, so Vc, so how to find, because you know C equal to Q by V, so V equal to V will be the Q upon C, so Q is the 100 micro and C is the 10 micro, that is micro cancel 10 volt. Okay, as you know that voltage across the capacitor, because you have a resistance, after switching voltage across the capacitor cannot be changed instantaneously, Vc 0 plus, it is not the special case, so 10 volt. Now after switching you have to see the how is the circuit. When after switching I see the circuit looks like this, is R and C. When I look, this is your I. So time constant, simply you see here RC. What is the R? 10 into 10 to the power 3. C 10 into 10 to the power minus 6. That is, you get here 1 upon 10. Yes or no? Yeah, 1 upon 10 second. Time constant unit is second. Okay. Then, okay, we got the Vc 0 plus. Can anyone say what will be the Vc infinity? Like capacitors will ultimately discharge because there is no forcing source here. Whatever the charge is there, it will be completely discharged through these resistors. So Vc infinity will be 0. Now we are in position to apply that relations. So Vc at any time t is equal to Vc infinity minus Vc infinity minus Vc 0. Okay, what we need to find? Vc. Okay, that's not issue. It you can also find out. Okay, that's not issue. We can, let's just find what Vc infinity. So Vc infinity is equal to 0 minus 0 minus 10 e raised to the power minus t upon tau. So e raised to the power minus t upon 1 upon 10. So you got 10 e raised to the power minus 10t volt. Similar fashion you can find out the current. I 0 plus will be the, when the switch is closed, the circuit is like this. So I 0 plus is the V 0 plus upon R. So V 0 plus is the 10 volt, R is the 10 kilo, that is 1 milliampere. I infinity by completely discharged, so no current flow, 0. So I of t equal to, and time constant remains same for the voltage and current, minus I infinity for the all the circuit variables, time constant remains same, I 0 plus e raised to the power minus t upon RC. So I infinity is 0 minus 0 minus 1 milliampere e raised to the power minus 10t. So finally e raised to the power minus 10t milliampere for t greater or equal to 0. Okay, I hope it is enough for you today. Please go through the, you will find the maximum number of questions, okay, from by using these relations. Once you understood it, you can easily able to do the question in the competitive exam. Okay, so see you in the next class. Till then, take care and good night, and keep practicing the previous year questions.